To write the final equation, what you're going to do is you're going to start with the function that's given. So for this first problem, your function is 1 over x. If I give you the order, so see how I'm giving you the order here? You have to follow the order that's given to get the final graph correct. So I'm going to take my original function and I'm going to move it to the right 4 units. So when I move something to the right 4 units, what that means is I do f, or my previous function, of x minus 4. So wherever I see an x in the previous equation, I'm going to replace it with x minus 4. So here's where I'm at. Now I need to reflect over the x-axis. So what I do is I take my previous step, we'll call f of x, and I reflect it over the x-axis. So that means I negate the entire thing. So I'm going to negate the entire previous equation. Now I need to move the graph up 3 units. So I take my previous equation and I tack on a plus 3 to it. See how I'm following the rules exactly? So I take my previous equation and I tack on a plus 3 to it. Then it says what will be the resulting equation. Well, we're done. So my final equation, usually you can call it something else, g of x is equal to negative 1 over x minus 4 plus 3. This will be my final answer. Notice you have to follow the order they give you. For this problem, we're going to start with this as our original function. We want to move it 5 units to the left. So I take my previous function and I move it 5 units to the left. So following that rule, we're going to move it 5 units to the left. This is f of x plus c from the horizontal shift section. Okay, so now wherever I see an x in my previous equation, I'm going to just replace it with x plus 5 squared. All right, now I need to reflect over the y-axis. So I take my previous graph, we'll call f, and I reflect it over the y-axis. So that means I negate my x, and I'm getting these right from the properties, so study those properties. Reflect over the y-axis. So wherever I see an x, what do I replace it with? Negative x. Then I have to move the graph down 1 unit. So I take my previous step and I subtract my c value from it. So we'll call this f. Subtract my c value, or 1, from it. Now it says I have to reflect over the x-axis. So when I reflect over the x-axis, I negate my y, or my entire function. When I negate this entire function, do you see that I have to distribute here? So this becomes negative this term squared. Notice how I'm not allowed to bring that negative side inside the squared binomial. And I have a negative times a negative gives me a positive 1. So my final graph, we'll call it g of x, is equal to this. Follow the rules and follow the order exactly. For my next problem, I'm given this as my original function. Now I need to move it 4 units up. Well, I take my previous step and I just tack on a plus 4 to it. So I get e to the x plus 4. Then move the graph 2 units to the right. What that means, 2 units to the right, is x minus f of x minus 2. So wherever I see an x in my previous equation, what do I have to replace it with? X minus 2, following the rules exactly. Bring down the plus 4. See how that x minus 2 is the exponent? Because I was just replacing the x with x minus 2. Now I have to reflect over the x-axis. So that means I have to negate the entire previous step. So I have to negate the entire previous step. Remember, you have to distribute. If you want to keep these in parentheses up here, you can, but you don't need to. Distribute. So your final equation is this. All right, again, this is my recommended order if you get to choose. So if you are given a final equation and I want to know how you got there from the parent function, you get to choose your order. If I give you a starting function and I tell you the list of transformations, you have to use the order I give you. All right, so now we're starting with the parent function. which means I get to choose the order. Notice how when I gave you the word problem, you had to do the order I gave you. All right, so now I'm choosing the order. I, again, like to do my horizontal shifts first, then my reflections, then my vertical shifts last. So I start with my parent function, and then I try to look for my horizontal shifts. So I replace my x with x minus 2. So wherever I see an x in the previous equation, I replace it with x minus 2. What does that mean? Well, that's just a horizontal shift to the right 2 units. And now it looks like I want to negate the entire thing. So when I negate my previous step, that's going to look like this. And remember, I cannot bring that negative sign inside those brackets. When I negate my entire function, or if I negate my y, that's going to be a reflection over x. This equation here matches this equation here. So this order on the left-hand side should be the correct order to take from the parent function to get to this final graph. How will I know I'm right? I'm going to check a few points by substituting them in. So I start with my parent function, just a little sketch. Then I move it to the right 2 units. And then I reflect over x. This is where I think my graph will be. So I'm going to erase my other previous steps. And now I need to check some points. 2, 0 should work. When I substitute in a 2 here, 2 minus 2 is 0. Negative 0 is still 0. So that works. Now let's check another point. 3, negative 1. See, I'm just choosing points on my final graph. When I substitute in a 3 here, I get 3 minus 2. The absolute value of that is 1. So I get the opposite of a positive 1, which is a negative 1. So that checks out as well. If you wanted to, you could check 0. When you substitute in 0, you get negative 2. Absolute value of negative 2 is 2. The opposite of 2 is negative 2. So that checks out as well. So you make sure your ordered pairs are actually solutions to your original graph. If they are, then the order that you chose was correct. A lot of students prefer to rewrite this so it looks more familiar to them. If you wanted, you can rewrite this equation like this. Again, I like to start with my parent function. And I like to do my horizontal shift. It looks like I'm going to replace my x with x plus 1. So that's what I'm going to try. Replace it with x plus 1. This is what I get. If I do that, and that's the correct first step, I would be moving my graph to the left 1 unit. To get from here to the final graph, what do I have to do next? Well, I have to reflect. I need to negate this x here, so I'm going to reflect over y. So how do I reflect over y? I negate my x. That's the rule for reflection over y. And again, I'm testing. I don't know if this is going to work. I have to see by using the equation to help me. Wherever I see an x, I replace it with a negative x. Okay, so it looks like we're off to a good start. Now I need to get this negative sign here taken care of. Well, that's negating the entire function. So how do I negate my entire f of x? Well, that's when you're reflecting over x. So you negate your entire function. Okay, and now I just need to tack on a plus 2 to my previous step. Well, that's a vertical shift up 2 units. So I take my previous step and I add plus 2 to it. This final equation here matches this equation here, which means if I follow these steps in this order, the graph of my final equation should be the graph of this equation here. So I'm going to do a rough sketch of my parent function. Okay, now I need to move it 1 to the left. Now I need to reflect it over the y-axis. Now I need to reflect it over the x-axis. Now I need to move each ordered pair up 2 units. Now I need to check to see if my final graph matches this equation. So I'm going to try the ordered pair 2, 3. Yeah, that's an ordered pair on my graph. So whenever I see an x in my original equation, I'm going to substitute in 2. So this becomes negative 1 on the denominator. So this is 2 minus 1 divided by negative 1. So this becomes negative 1. 2 minus a negative 1 is really 2 plus 1. So I get 3 as my output. So that ordered pair does work. So now I want to check at least one more ordered pair. Notice how the shape of my graph remains very, very similar to the original. So the other ordered pair I'm looking at is 0, 1. So whenever I see an x in the original equation, I'm going to substitute in 0 and see if I get 1 for the final output. So this is going to be 2 minus, this equals 1. 1 divided by 1 is 1. So 2 minus 1 is equal to 1, which matches the output we expected. So this graph here in purple should be the graph of the original equation. If I ask you to describe the order, this would be your answer. If I asked you for the parent function for this one, that would be your answer. All right, so to be able to graph this easily, we have to figure out what the parent function is. And then we have to follow the steps of our transformations. So here's our parent function, the most basic we can get. And again, I like to do left or right first. So I notice that I'm going to substitute in x minus 1 wherever I see an x to get closer and closer to this final equation. When I substitute in x minus 1 wherever I see an x, I'm really moving my graph to the right 1 unit. So see how I'm recording the order as I go. Okay, so now I take my previous step, and what do I have to do to that? Well, I have to negate the entire thing. If I negate this entire thing, this is what I'm left with. So when I negate y, or my entire function, that's a reflection over x. So now, how do I get from here to my final equation? I just have to tack on a plus 2. So I take my previous step and I add 2 to it. So I get negative square root of 3 of x minus 1, negative cube root of x minus 1, all plus 2. Does this match my original equation? If it does, this order right here should make the entire graph of this equation. So I start by plotting my parent function. This would be like 8, 2 over here, and this would be like negative 8, 2. So you can see how slender it is. All right, so here's my sketch of my parent function. So I have the 3 main points. Those are the main points I'm going to focus on, and then the shape. So then I need to move this to the right one. Notice how I transfer the points and then the shape. And now I need to reflect it over the x-axis. So reflect 1 away, stays the same, reflect 1 away. And now I reflect the shape of it. All right, and now I need to move this graph up 2 units. Up 2 units, up 2 units, up 2 units. And then I take my shape of my graph. All right, I think the final graph is in blue here. So I'm going to check a few points, 1, 2. Wherever I see an x in my equation, I'm going to substitute in a 1. 1 minus 1 plus 2. So this becomes 0, 0, negative 0, 0. 0 plus 2 is 2. So that works out. So now I need to check 2, 1. Wherever I see an x, I substitute in a 2. 2 minus 1 is 1. Cube root of 1 is 1. The opposite of 1 is negative 1. Negative 1 plus 2 is equal to 1. So that works out as well. And if you want to do some extra checking, you can plug in one more point for fun. You can plug in, let's say, 0. The cube root of negative 1, well, what times itself equals negative 1? Negative 1. The opposite of that, plus 2. So you get 1 plus 2, which is 3. So 0, 3 also works. So this graph in blue is the graph of this original equation. These are the list of transformations in their proper order, and this is the parent function. If I ask you to state the parent function for this graph, you're just looking for the most basic. Then you want to state your transformations to get to your final function. Your answer must be in a proper order. Remember how I said there are more than one correct answer for some of these problems. So it's not my way or the highway. If you don't like my order of the transformations, you don't have to use them. but it will help you with your signs. So I highly recommend it, but there are other correct answers to get to the final graph of this equation. Okay, so now here's my parent function. Now I need to figure out how to get to here. I like the horizontal shifts first. So wherever I see an x, I'm going to replace it with x minus 2. All right, well, what kind of change is that? That's to the right 2. And then I have to negate the entire thing. So I'm negating my previous step. That's a negation on y, so that's going to be a reflection over x. Then I have to subtract 1 from the entire function. So I take my previous function and I subtract a 1 from it. And that's just a vertical shift down 1 unit. So what do I think the order of my transformation is? Well, I think it's right here because this equation matches this equation now. All right, again, proper order. A lot of students like to rewrite this so it looks more familiar to them. What kind of 5 is that? Plus 5. All right, so a lot of students like to rewrite it like this. Now we need to identify our parent function. Our parent function is just going to be x squared. Okay, so now how do I get from here to here? Well, I replace my x with x minus 3. Wherever I see an x, I replace it with x minus 3. Okay, I'm getting closer. Now I have to negate my entire previous step. Negate my entire previous step. That's a reflection on x. The previous step was moving to the right 3. And what's the last step? Well, it's a vertical shift up 5. I take my previous function and I add 5 to it. Take my previous function and I add 5 to it. Does this equation match the original equation exactly? If it does, we are good to go. This would be my final answer. This would be the list of transformations to get from the parent function to this new function. Remember, the order matters. All right, your original function here, your parent function, is going to be the absolute value of x, the most basic you can come up with. Now again, a lot of students like to rewrite this. You can rewrite this as negative x. What kind of 2 is that in there? Positive 2. Bring down the minus 5. If you like to rewrite it so you can see the patterns easier, feel free. So I'm going to replace my x with x plus 2. So that's going to be a shift to the left 2 units. Now, how do I get to the final graph? Well, I need to negate my x. So wherever I see an x and I negate it, that's a reflection on y. So wherever I see an x in the previous step, I'm going to replace the x with a negative x. I'm getting closer. Now I need to take care of that negative sign in front. I need to negate that entire function. So that's going to be a reflection on x, right? I'm negating the y, so it's a reflection on x. Negate the entire previous step. Then you just have to tack on the minus 5 to the previous step. So that's a vertical shift down 5 units. So I think this is the description. Let's see if this equation here matches the original equation. If it does, we are correct, and this should be my final order. To complete the square for a quadratic, we're going to be working on one side of this equation. So my first step is to factor out my a value just like it was before. But for this problem, the a value is just 1, so I get to leave it alone. So I get x squared minus 6x. I leave my first space here, bring down the plus 11, leave my second space here. How do I get the value to make this a perfect square trinomial? Well, I take half of my new b value, which is negative 3, and I square it. So I get a plus 9 here. Now, we just made a perfect square trinomial, which means it should factor into something plus something squared or something minus something squared. All right, now I need to balance my equation. So I just added in a 9 to the right-hand side. If I need to do something else to the right-hand side, what do I have to do to it to balance the equation? Well, I have to counteract it. Why do I counteract it? Because I'm working on the same side of the equation. All right, so my next step, I get f of x equals x minus 3, right? I'm just factoring that perfect square trinomial squared plus 2, combine my like terms over here. Now we have it in this form. H and K are going to represent what's called the vertex of your parabola, it's your turning point. So I want to see if we can get from this equation to my final equation, thinking about the shifts. Well, I'm moving to the right 3, because I go from x squared to x minus 3 squared. And then I'm moving it up 2, because I take my previous step and tack on a plus 2 at the end. Since this matches the final equation, I can go ahead and graph my parabola. So I do a quick sketch here, then I move it to the right 1, 2, 3 units. Again, quick sketch. And then I move it up 2 units. So I take this point up 2 units, up 2 units, up 2 units, up 2 units, up 2 units. Sketch my final graph. And double check it. You can double check with the original equation or you're completed the square form. If I was double checking, I would probably substitute into the original just to make sure I didn't make any errors when I was completing the square. When I substitute in a 3, I think I should get 2 out. So 3 squared is 9. 3 times negative 6 is negative 18 plus 11. So this becomes negative 9 plus 11, which is 2. So that works out. Again, try another point just to make sure. Point to the right of the vertex. See how the vertex is the turning point? 3, 2. That's your turning point. That's called your vertex. That's your H, K. Now, I want to try one more point. A point to the right of your vertex. So a point to the right is 1 to the right of 3, which is 4. So I think I'm going to get 4, 3. Let's see if I do. 4 squared is 16 minus 24 plus 11. 24 minus 16 plus 11. Negative 8 plus 11 is 3. It works. This purple graph here should match the original equation. So if you complete the square, you can find the graph of your final function very easily by using the transformations. So you can see the shift to the right and left and the vertical shift and possibly reflections. When you're completing the square with an a value that's not equal to 1, remember you have to factor that out first. So you factor out your a value, you're left with x squared. Negative 4x divided by a negative 2 is a positive 2x. You leave your space, bring down the minus 1, leave your space again. All right, now you need to figure out what to put here. Well, half of your new b squared. So 1 squared is just plus 1. Now, did you really just add a 1 there? No, you actually subtracted 2, right? Negative 2 times 1 is negative 2. You actually just subtracted 2. So what do you have to do to counteract a subtraction from 2? You have to add 2. So you're counteracting what you just did before. So negative 2 times x plus 1 squared, so I just factored this trinomial, bring down the combination of these two. So now it's in completed the square form. You'll be able to find your vertex by doing the opposite of this value, keep the sign of this value. So I think my vertex is going to be at negative 1, 1. Now if I was thinking about this, I would say, okay, well my original graph starts like this, and then I move it to the left 1, and then I negate the entire thing, so that's a reflection over x, and then it says I add 1 to it. So I think I'm going to be like this. So that final graph I drew, that's where I think I'm going to be. So that's my idea. So if I have a negative 1, 1, how do I figure out the points to the right and left? Well, when the a value is 1, I already know the points to the right and left. It's based on the parent function. But when the a value is not equal to 1 or negative 1, what I have to do is plot a point to the right of my vertex. So my vertex is at negative 1, 1. So a point to the right would be 0, something. Well, if I substitute in 0 to the original equation, I'm going to get 0, 0, minus 1. So I'm going to get -1 out. So at 0, -1, I should have an ordered pair. The nice thing about quadratics are they have a nice line of symmetry here. So I can reflect that point over. Now if I wanted a better sketch, I could substitute in another value to the right. So what's another value to the right of 0? 1. See, I'm sticking pretty close to the vertex, as close as I can, while using integers. So I have -2 times 1 squared, which is just 1, minus 4 times 1, minus 1. So I have -2 minus 4 minus 1, so I get -6. -6 minus 1 is -7. So 1, -7, I'm down here, and I can reflect it right over my what's called an axis of symmetry. So you plot your turning point or your vertex using h comma k. Find a point to the right, reflect it over. Find a point to the right again, 1 comma -7, and reflect that over the axis of symmetry. The original graph of f of x is shown below. See if you can find the graph of f of x plus 2. Well, f of x plus 2 is just a shift to the left 2 units. So I take all my ordered pairs and I shift them to the left 2 units. 2 units. And then I keep my shape. So if I asked you to graph f of x plus 2, this would be your final graph. If I asked you to graph f of x plus 2, you'd have to notice that this is a vertical shift up 2 units. So I take all my ordered pairs and I move them all up 2 units. And then I connect for their shape. Now, if I were graphing f of -x, I would have to know that's a reflection over the y-axis. Here's the y-axis. So I reflect every point over. This is 1 away, so it's 1 away. 3 away, so it's 3 away on the other side. This is 4 away, so it's got to be 4 away on the other side. This is 6 away, so it's got to be 6 away on the other side. And then I kind of bring my shape across. Notice how it looks like a mirror. The y-axis looks like a mirror. All right, negative f of x. I'm going to take my original function and I'm going to reflect. So I change the y to -y, so I reflect over x. Here's the x-axis, and I have to reflect over it. 3 away on the other side. 2 away on the other side. 2 away on the other side. 5 away on the other side. And then I connect my shape. And now the line that should be the mirror is now actually the x-axis. As you could see on the previous problem with our parabola, there are vertical stretches and compressions. If you want to find the graph of a vertical stretch, you'll have a constant times your original function. If that constant is greater than 1, so if I have like a 2 times my original function, I will have a vertical stretch. So if my graph looks like this, I'll have a vertical stretch. If my c value is between 0 and -1, I'm going to have a vertical compression. So I'm going to give you a few examples of what that will look like. If I graph my original function, f of x equals x squared, and 2 times x squared, so 0, if I plug in a 0, I get 0. If I plug in a 1, I get 1 squared is 1, 1 times 2 is 2. If I plug in a 2, 2 squared is 4, 4 times 2 is 8, so I'd actually be all the way up here. I can reflect them over or plug in more points. So notice that when the a value is greater than 1, I have that vertical stretch. When I plot this, I plug in 0, I get 0. When I plug in 1, I get 1/2. When I plug in 2, I get 4. Half of 4 is 2. And you'll see that vertical compression. If the constant is attached by multiplication to the input rather than the output, there's going to be a horizontal stretch if the c value is between 0 and 1, and there's going to be a horizontal compression if the c value is greater than 1. So here I'm going to plot my parent function. Now I'm going to plot this in blue. Square root of 0 is 0. The square root, if I plug in a 1, I get the square root of 1/2. I don't feel like graphing that, so I'm going to try 2. When I plug in a 2, I get the square root of 1, which is just 1. The next nice value I'd plug in would probably be 8. So see how the graph is horizontally stretched when this constant is between 0 and 1. Square root of 0 is 0, square root of 9 is 3. Compression.